networks and telecommunication domain, where I designed end-to-end network architectures for our global clients. Later, I transitioned onto the software side of the business, where I primarily focused on delivering software applications that provided functionalities such as secure messaging, secure push data, and secure notification to our end users. Later, I transitioned into the robotics and AI space, where I was responsible for orchestrating product demos and launches for our clients in the global markets. With that as a background, now I would like to provide a high-level overview of key topics we'll discuss in this course. First, we'll learn how the internet works. What happens when you send a message to your friend on WhatsApp? How is that message transmitted from your phone to your friend's phone over fiber cables through multiple data centers and cloud computing platforms? Second, we'll take a look at some of the basic components you will use to build a system. We'll discuss the pros and cons of each component, and we'll discuss when to use which component. Last but not the least, we'll discuss the standard framework you will use to build systems from scratch. We'll also cover some real-life case studies of systems that have been developed in the industry. Now let's get started. Hi there, this is Pratmesh, and in this session we'll discuss how the internet works. Before we learn more about internet, let's try to understand how postal services work. In this example, our friend Mary is located in Texas. She wants to send a package to her friend Jim, who lives in New York. What does Mary do? Mary packs a package, adds her name and address, and also adds Jim's name and address, and heads to the post office. The team at the local post office accepts this package and selects appropriate channel, such as ground, air, and sends the package to Jim's post office. Once the package is received by Jim's post office, it's delivered to Jim's house. Now, if you understand how postal services work, let's try to understand how the internet works. Replace the post offices with data centers that are managed by internet service providers. Instead of a package, Mary will now send a digital message. Let's say Mary is using a web app on her laptop to send a message to Jim. Mary types, "Hi Jim," using her keyboard. Her laptop takes this text as an input and converts this into a binary information. This information is further converted by her laptop into a radio frequency signal, which connects her laptop to her Wi-Fi router. Her laptop also adds her IP address of her laptop to this digital packet and forwards this packet to the Wi-Fi router. The Wi-Fi router further converts the signal into a photon, which is nothing but light packets, and transmits the signal over fiber cable to the corresponding data center. These data centers are equipped with different routers. They use Jim's IP address listed in Mary's packet and route the signals towards Jim's internet service provider over fiber cables. Thus, the message is delivered to Jim. If you understand this concept, now let's see how the internet works at a national scale. The internet at a national scale is a network of networks. Each network is managed by an independent ISP. Each ISP owns numerous data centers and fiber cables that are connected to these data centers. In this picture, you will see the logical internet map for the US. Here, we have numerous ISPs such as Verizon, AT&T, Comcast, Xfinity, etc. Each of these ISPs own multiple data centers and they are connected to each other over fiber cables. The orange lines that you see in this picture are essentially the fiber cables that connect these data centers. Thus, they help us send packets from one city to another. Now let's take a look at the logical internet map of the world. This is a trimmed down version of the internet map of the world. Here, you will see the same concept holds true. Starting from the left, you will see the data centers in the US are connected to the data centers in Europe and Canada through submarine cables. Similarly, the data centers in the EU are connected to the data centers in Asia via an array of submarine fiber optic cables. Thus, we are able to exchange messages over the internet with our friends in different countries. Now, if you understand this, let's see what goes in each of these data centers that are located on this particular slide. Each of those data centers that you saw on the previous slide include a rack of servers and network equipment. Each rack can hold anywhere between 15 to 20 devices. Servers are primarily used to host web applications. This is where all your profile data, social media pictures, posts, etc. are stored. Routers, on the other hand, are used to transmit this data from one data center to another and to end users. Firewalls, on the other hand, are the cops of the internet world. They comb the data and ensure only authorized individuals are able to access your data. If you understand this, now let's take a look at the real map of the internet. The map that you see on the left of this slide is essentially the real map of the internet. The circles on this map represent data centers owned by different internet service providers. The colored lines on this map represent the fiber optic cable that connect these data centers. The next time you send your message to your friend in Europe from the US, remember, you are actually sending an array of photons over fiber optic cable located on the floor of North Atlantic Ocean. Now, let's summarize what we have learned so far. We learned Internet is essentially a network of networks. Each of these networks is owned by an internet service providers. There are numerous internet service providers around the world, such as Comcast, AT&T, Vodafone, and NTT. Each network consists of numerous data centers. These data centers are connected to each other by fiber cables. Each data center consists of numerous racks of web servers, database servers, routers, and firewalls. These devices communicate with each other using internet routing protocols. That's it for this session. I hope you enjoyed it. I'll see you in the next session. Stay tuned. Hi there, this is Prathamesh, and in this session, we'll discuss the building blocks of the modern day software systems. These are known as system components. Before we take a look at each of these components, let's try to understand what components mean in the context of building a skyscraper. Let's say you are building a skyscraper. What are some of the questions you will ask yourself? Who are we building this skyscraper for? How many units do we need to add to this skyscraper? Are we building this skyscraper for commercial use or for residential use? Then you will decide on the different types of components you will need to build this skyscraper. Some of the other questions you will ask are, what kind of flooring do I need to use? What kind of bricks should I be using? What kind of metal bars do I need to ensure the foundation of my skyscraper is strong? What kind of tools and machinery do I need to build a skyscraper? Last but not the least, what are the pros and cons of using each of these components? Once you have finalized the components, you will end up putting together a detailed plan. That is, a framework to design and build this skyscraper. Similarly, in the world of software systems, you will need to understand the components and framework to design systems that are highly scalable, available, secure, and reliable. So, in this course, you will learn some of the following components. First, what is a load balancer? How do I ensure I do not put too much load on one server? The answer is we'll need to use load balancer. Second, how do I ensure my users are able to load their content with minimal latency? The answer is CDN, Content Delivery Network. Third, where should I store all my data? The answer is databases. Fourth, where should I store my frequently used data? The answer is RAM, cache. Last but not the least, how do I ensure one software service is not impacting the performance of another software service? In other words, how do I decouple my software services? The answer to that question is we'll use message queues or buffers. And in addition to components, you will also need to learn protocols. What procedures should I be following to implement each of these specific features, such as video streaming, audio streaming, email, bank transactions? The answer to that question is protocols. You need to select appropriate protocols that deliver this functionality. Now that we have a high-level overview of each system component, let's try to learn each of these components in detail That's it for this session. Hope you enjoyed this session. I'll see you in the next one. Stay tuned. Hi there, this is Prathamesh, and in this session, we'll learn more about load balancers. Before we take a look at load balancers, let's try to understand how banks provide service to its customers. The last time when you visited a local bank, you may have noticed a teller, also known as a cashier. They essentially serve customers by completing account transactions. They provide services by receiving deposits and loan payments, cashing checks, and issuing savings withdrawals. Each of these transactions can take anywhere between 2 to 10 minutes. Now, if you have 100 people standing in a queue, the teller who is providing the service will soon be overwhelmed and may not be able to provide service to customers in time. In order to resolve these issues, banks provide a service which is similar to a load balancer. In this case, instead of one teller, there will be multiple tellers who will provide service to end users. Now, the work of providing the service to customers is distributed amongst 3 tellers. This distribution is done using a load balancer. In this case, one of the bank employees will route customers to appropriate tellers and will play a load of a load balancer. Thus, they are not able to provide timely service to customers, but they are also ensuring that none of the tellers are overwhelmed and exhausted. This improves their performance and customer service. Now let's take a look at the software systems. Let's say multiple users are trying to access a web-like Gmail app. In this case, if there was just one Gmail server in the world and all the servers were trying to access this server, that would greatly impact the performance of this server and will result in long delays. How can we solve this problem? A new friend load balancer comes to our rescue. What if we added a load balancer in front of these servers? Now the load balancer will distribute incoming requests amongst a group of servers. Thus, the users are no longer required to wait in the queue, since we are able to scale our systems and serve more users. So, here are the benefits of using a load balancer. Load balancer allows us to add more servers as needed, and thus we can easily scale our web apps as we add more users to the system. Next, it improves availability. If one server goes down, the load balancer can forward the corresponding traffic to another server and thus it prevents outages. This will ensure our users are not impacted due to an outage of one or few more servers. Next, it also improves latency. Due to the addition of new servers, requests are now processed at a faster pace since more servers are able to serve end users. This minimizes delay and ensures real-time service for our end users. Last but not the least, it also provides reliability. An outage of one server won't impact the performance of another, and hence we are able to maintain a high reliability with the addition of a load balancer. Now let's take a look at some of the algorithms that are used by a load balancer. So the first algorithm that we're going to discuss is round robin. In this case, the requests are distributed in a sequential manner. First, the request is received by the load balancer, then it is forwarded to server 1. The next request that is received by the load balancer will be forwarded to server 2. The following one will go to server 3, and the exact same pattern will be followed to handle the next set of requests. This is a simple algorithm, but what are the downsides of using this algorithm? It assumes all the requests that are handled by the load balancer are equally heavy, meaning all the requests will consume same amount of CPU power and hard disk power. In reality, that's not the case. Request 1 could be related to some social media post and may need a low power. On the other hand, request 2 could be related to a video call which is made by another social media user and may need high power on the CPU and the RAM side. Posting a message on the social media is a simpler request and will need less number of resources versus a live streaming session that will be joined by 1000 users. To solve this problem, we can use the least resource algorithm. Let's take a look at that. In this case, the incoming requests are sent to the server that has a maximum number of free resources, such as CPU power, hard disk capacity, RAM, etc. In this example, you can see server 1 has only 20% resources that are utilized, server 2 has 90% resources that are utilized, and server 3 has 10% resources that are unutilized. So, in this scenario, clearly, server 2 has maximum number of free resources and hence this incoming request is sent to server 2. I repeat, server 1 has 20% resources that are not utilized, server 2 has 90% resources that are not utilized, server 3 has 10% resources that are not utilized. Hence, in this case, server 2 is the server that has the most number of resources that are available. So the incoming request will go to server 2. With that being said, let's take a look at the next algorithm. The third algorithm that we have is known as least connections. In this scenario, incoming requests are sent to the server that has the least number of connections. Let's say server 1 is handling 10 requests, also known as connection. Server 2 is handling 1 request, and server 3 is handling 1000 requests. Now, the incoming request received by the load balancer will be forwarded to server 2 since it's only processing 1 request at the moment, while the remaining servers are processing way more requests. So, in this scenario, requests will always go to the server that is processing least number of requests at any given point of time. If you understood this, let's take a look at the last algorithm. This algorithm is known as IP hash. This is a simple algorithm. In this case, all the incoming requests will be routed to different servers based on the IP address that is mentioned in that request. The advantage of using this algorithm is, let's say if you have a web application where you want to ensure that the requests that are received from a certain set of IP addresses are given to server 1, the next set of requests that are received from a certain set of IP addresses are handled by server 2. So you can do a mapping of IP address to server using this algorithm. The advantage of this algorithm is this comes handy when you have an application where you have to do this kind of mapping between an IP address and the server. The disadvantage is you will have to keep a track of every IP address, of the request that is received from the client, and that can add a little bit of a delay. So, with that as a background, let's move on to our next slide. So, in summary, we have studied what a load balancer is, when to use a load balancer, what are some of the benefits that a load balancer provides. We also learned that using a load balancer is more of an art than a science, and choosing an appropriate load balancer is a key. Choice of appropriate load balancer is key for a strong system design. When you choose a load balance algorithm, you are essentially making a trade-off on simplicity of execution versus application performance. Typically in the industry, round robin and least resources are the two algorithms that are commonly used. That's it for this session. Hope you enjoyed this session. I'll see you in the next session. Stay tuned. Hi there, this is Prathamesh, and in this session, we'll learn more about CDNs, also known as Content Delivery Networks. Before we try to understand what CDN is, let's try to understand what happens when you try to stream an animated movie over streaming apps such as Netflix, Hulu, etc. Let's say you're designing a new streaming platform such as Netflix, Disney, and Hulu for animated movies. Let's assume you store these movies on a server, and let's assume the server is located in the US. Let's assume one of our users is located in Asia and is trying to stream this movie on their local laptop. This user is frustrated because it's taking them a long time to load this movie on their laptop. I'm sure you must have been in a similar scenario. Well, the question is, how do you solve this problem? We can solve this problem using content delivery network. Let's assume you have connected your server to a CDN network. Typically, a CDN network consists of numerous servers that are located in different regions across the world. Now, when you try to request a movie from a central server, the central server will track your location using your IP address and will redirect you to a CDN server that is located close to your physical location. You will then be able to happily stream this movie with minimal latency. Thus, CDN allows you to reduce latency of your system by ensuring your static assets such as images, videos, and files are located close to end users. This greatly improves the performance of your application. This is what a typical CDN integration looks like. Typically, you will host your application on a web server. Let's call it a central server. Let's say the central server is located in the US. You will connect this central server to a CDN network typically provided by Google Cloud, Akamai, Amazon CloudFront, or Cloudflare. Once your central server is connected to these CDN networks, you will be able to keep a copy of your static assets such as videos, images, and files on these CDN servers. Thus, your users will be connected to the CDN server that is located close to their physical location, and hence they'll be able to access corresponding data with minimal latency. Now let's take a look at different types of CDN algorithms. There are two basic types of CDN algorithms, push and pull. CDN algorithms decide how frequently you are going to transfer your data, that is movies, images, and files from your central server to your CDN servers. Let's try to understand how a push type of CDN works. In this case, the central servers will push proactively the data to CDN servers at a fixed amount of interval, let's say 1 hour, 5 hours, etc. Advantage of this type of algorithm is that this will ensure the data that is located in the CDN servers is the latest and the greatest data and is frequently synced with the core servers. Thus, this algorithm improves your application performance and customer experience. The disadvantage of using this algorithm is that this service comes at a higher price. Now let's take a look at the second type of algorithm, which is known as pull CDN. In case of pull type of algorithm, the CDN servers will request the data from the central server only if the data that's requested by the end user is not available to the CDN server. Meaning, if a user tries to access the data and that's not available on the CDN server, that's when the CDN server will reactively try to access the data from the central server. The advantage of this type of algorithm is that this service is relatively cheap compared to pull service, but can introduce delay and thus impact customer experience. So, how does one choose the type of CDN algorithm and service? You would always want to check the price of CDN push and pull service offered by different vendors and make a choice based on your budget and requirements. System design is all about trade-offs, and while choosing an element, you'll always have to make a trade-off. Now let's summarize what we have learned so far in this section. First, we learned CDN allows you to reduce latency associated with your applications by ensuring the data is stored close to the end user. This also reduces the burden on your central database servers, since users are not trying to fetch the data from the central database servers, but they are always connected to the CDN servers close to their physical location. Secondly, you will learn there are different types of data that can be stored on CDN servers, such as video files, audio files, images, and static assets such as your website logo. We also learned the pros and cons of using push versus pull type of CDN service. There are different types of CDN providers that are available today, and some of those common ones are as follows: Amazon CloudFront, Google CDN, Cloudflare, etc. You must be wondering how Netflix implemented a CDN service to distribute movies and TV shows. Let's take a look at that. So Netflix implemented its own CDN service architecture, and it's known as Netflix Open Connect. Netflix started this initiative in 2012. In 2011, as a response to the ever-increasing scale of Netflix streaming, Netflix wanted to proactively store its content close to its end users and provide a better performance to its users. In this initiative, Netflix works with different ISPs, internet service providers, and continuously optimizes its Open Connect architecture. For more information, please access the link listed in this slide and you will learn Netflix's way of implementing and scaling a content delivery network, also known as CDN. That's it for this session. Hope you enjoyed this session. I'll see you in the next session. Stay tuned. Bye. Hi there, this is Prathamesh, and in this session, we'll learn more about cache. Before we try to understand what cache is, let's try to understand how a coffee shop works. Let's assume our friend Bob has started a new coffee shop. Let's assume Bob was so busy building his shop that he forgot to install a price board that would have helped people learn about the price of different types of coffee that his shop sells. Customers arrive at the shop and frequently ask for the price of different types of coffee. Bob doesn't remember the price and he frequently checks his laptop to see what the price is, and this adds a lot of delay. Customers realize it takes too long for Bob to respond and they start heading to a different shop. What can Bob do to solve this problem? You guessed it right. Bob can now install a board on the top of his shop that would help customers understand the different types of coffee that is served at his shop and the corresponding prices of each type of coffee. Bob installs the board and his customers are now happy. Thus, Bob has minimized the delay and now can process the order at a faster pace. In theory, Bob has cached the price of coffee. Price of coffee was a frequently requested information and Bob has managed to put it on a board and made it easy for customers to access, thereby minimizing the delay and improving the performance of his shop. Thus, cache is actually a hardware or a software that can store data that is either frequently requested or needs a lot of computation power and time. Cache works on the locality of reference principle. Frequently requested data is likely to be requested again, hence, it makes sense to store this data in cache since the cache is faster compared to hard disk. Now that you know what cache is, let's try to understand how a computer works. Let's say your computer CPU is trying to access data from hard disk. CPU typically has a higher speed, somewhere in the range of 1.8 to 4 GHz. Your hard disk, on the other hand, is slow and typically runs at 5 to 10,000 RPM. Now, even though you have a CPU that is fast, your hard disk is still slow, and hence, any data that needs to be extracted from the hard disk will take a huge amount of time. How can we solve this problem? You guessed it right. How about we add a cache or RAM? Let's say you added RAM. RAM runs at a speed of 1.6 to 3.2 GHz. Now you can store the data frequently requested by CPU in the RAM. And now CPU can access this data with minimal delay. Wait a minute. These days, CPUs include a lot of cores. Now each CPU will need a certain amount of RAM to access this data. How do we solve this problem? Let's say we have a quad-core CPU. We can solve this problem by adding a static RAM, also known as CPU cache. The CPU cache is further classified as L1 cache, L2 cache, and L3 cache. You will need to remember that the speed of L1 cache is higher than the speed of L2 cache. The speed of L2 cache is higher than the speed of L3 cache. The speed of L3 cache is higher than the dynamic RAM or DRAM, and the speed of dynamic RAM is higher than the hard disk. Also, the cost of dynamic RAM is lower than the cost of static RAM, but the speed of static RAM is higher than the speed of dynamic RAM. Simple reason for this behavior is that dynamic RAM includes capacitors, and capacitors leak charge, so they need to be frequently recharged, whereas static RAM is made up of pure transistors, which are much more efficient than capacitors, and hence static RAM is faster than dynamic RAM. Now that you have learned what CPU cache is, Let's try to understand what application cache is in the context of system design. Let's say you have three users, user A, B, and C, and all these users are trying to use an e-commerce app. Let's assume this e-commerce app is hosted on this app server. Let's assume all these three users are trying to access the price of a popular electronic device that's available on this e-commerce app. Let's say this price is actually stored in their database server. Every time a user makes a request for this price, the request is relayed to the database server and the response is sent back to the user. Now imagine if you have 1 million users trying to access this price. That is going to overload the database. Not only that, database is slow in terms of responding back, and hence that's going to degrade the application performance. How can we solve this problem? We can solve this problem by adding a cache. So we know from our course that cache works faster than database, and hence we can now store the price of frequently purchased items in the cache server. Now when the user makes a request to the app server for the price and the description of a popular electronic device, the app server can first check if this information is available in the cache. It can then pull this information and relay the same to the end users. Thus, cache was able to reduce the latency and improve the performance of our application. Now you may wonder, why not store all the data in cache? Well, the answer is simple. Cache solves our problem, but it's an expensive memory. Hence, we should only store data that is frequently utilized in cache, or data that needs a lot of computational power and time. Now let's summarize what we have learned so far in this session. We learned cache is a short-term memory and can be used to store data that is frequently requested or to store data that can be pre-computed and served to end user with minimal latency. Cache reduces latency and also reduces the load on our database server. Cache works by storing frequently used data and thereby minimizing the load on database server. We also learned that L1 cache works at a higher speed compared to L2 cache. L2 cache is faster than L3 cache, and L3 cache is faster than dynamic RAM, and dynamic RAM is faster than hard disk. We also learned that cache in general is faster than database servers, but it is also equally expensive. Hence, it should be utilized accordingly. I hope you enjoyed this session. With that as a background, now I'll see you in the next session. Stay tuned. Bye. There, this is Prathamesh, and in this session, we'll learn more about databases. Before we try to understand what a database is, let's try to understand how we use spreadsheets. Let's assume our friend Bob owns a warehouse. Bob has to keep a track of a large number of items in his warehouse. As Bob continues to scale his business, this problem only becomes worse. What should Bob do in his days? What should Bob do in this case? Turns out Bob has a friend Jim. Jim comes to Bob and recommends that Bob use spreadsheets to track his data. Bob starts using spreadsheet but realizes the following limitations of spreadsheets. Spreadsheets cannot scale. There are limitations on rows and columns in spreadsheets. Bob will need to maintain an array of spreadsheets to store his data. How can Bob solve this problem? You guessed it right. Bob needs to use a database to store his data. In this session, we are going to learn what a database is. We'll also look into the types of databases, relational and non-relational databases. In the next session, we'll also learn more about different types of databases and which database to use when. Let's try to understand what a database is. Database, in simpler terms, is an organized collection of data stored and accessed electronically from a computer system. There are two main types of databases, relational and non-relational. In case of relational databases, data is usually stored in tables, rows, and columns like a spreadsheet. Non-relational databases use a storage model optimized for specific requirements of the type of data being stored. There are different types of storage models, and we'll take a deep look into each of these models in the next session. So, here is what we have learned so far. We learned how Bob was able to solve the inventory management problem by using a database. We learned what a database is. We also learned why we need a database. The database allows us to store data in an organized manner, and this makes it easier for us to analyze, modify, and manage our data. We also learned there are two types of databases, namely relational and non-relational database. We use relational database when we have use case that needs ACID compliance or use case where we are looking for guarantee of transactions such as healthcare and payment gateways. That's it for this session. Hope you enjoyed this session. I'll see you in the next session. Stay tuned. This is Prathamesh, and in this session we'll learn more about relational databases. Let's take a look at the relational database. Relational databases, also known as SQL databases, use tables to store data. Each table consists of multiple rows and columns. Each row stores information related to one user. It's also known as record. Data from multiple tables are linked using keys. Key is a unique identifier assigned to each row in the database. Before we try to understand when to use relational databases, let's try to understand database transaction and ACID properties. A database transaction is a sequence of operations that acts as a single unit. If a transaction succeeds, the data that was modified during the transaction will be stored in the database. Transferring money between your bank accounts is an example of a database transaction. Relational databases comply with ACID properties. Hence, it's crucial to understand what ACID properties are. ACID is a set of guideline properties that ensure database transactions are processed reliably. Now let's take a look at the first of the four properties. Atomicity is the first property. The transaction should be completely executed or should be declared as a failure. So, if a database complies with this property, then in that particular scenario, the transaction that is processed by the database will either be completely executed or will be declared as a failure. Meaning, if one part of the transaction fails, the transaction will be declared as a failure by the relational database. In case of failure, the database will roll back the data to its original states that was maintained prior to the failure. So that's what ACID property basically helps us understand. With that as a background, now let's take a look at the next property, which is consistency. In case of consistency, basically what it dictates is the database should never enter an illegal state. If it does, the entire transaction should be cancelled and the database should be restored to its original state. Let's take a look at the example. All customer bank accounts, let's say, must maintain a positive bank account balance. Now, if a transaction is going to result in a negative account balance, it should not be processed. So that's one example of the property which is known as consistency. Now, if you understand consistency, let's take a look at isolation. In case of isolation, each transaction should not have any impact on another transaction. What this dictates is that in case of your database transaction, no matter how many transactions you are performing at any given point of time, none of your existing transactions should impact any simultaneous transactions that are being made in the database. So any read or writes performed on the database will not be impacted by other reads and writes of separate transactions occurring on the database at the same time. Let's take a look at the example. A person should not be allowed to withdraw and deposit the money at the exact same time. They can do so in a sequential manner but not in a parallel manner. That's where your isolation property comes into picture. Now, if you understood what an isolation property is, let's try to understand the next property, which is known as durability. What durability dictates is, once a transaction is completed, changes are persistent in the database permanently. Successful transactions are recorded on a permanent storage device such as hard disk. What this means is, if there is an outage, let's say there is a power outage, an outage of a database instance won't have impact on the data since the data is actually stored on the hard disk and it will persist. Meaning, once you recover from a power outage, you'll be able to power on your hard disk and recover your data. So that provides you with this durability property. Now you must be wondering, Prathamesh, how do I know what database to use when? In this scenario, we are going to focus on relational database. You use relational database when you have a fixed schema or fixed attributes. What I mean by that is, let's say if you're storing information about all the students, then if you know that you're only going to store the name of the students and the courses that they are enrolled in, that's a fixed schema. So if you know your schema ahead of time, you can use relational databases. Next, if you need asset compliance, we just saw all the asset properties. If you are looking for asset compliance, you should go with relational database. Last but not the least, if you're looking for guarantee of transaction and integrity, that's where you should go for relational databases. What I mean by guarantee of transaction is this. A transaction will be considered successful if all the database servers storing the corresponding data show exact same value. Meaning, if I deposited $100 in my bank account this morning, and my balance is let's say $100, it doesn't matter whether I connect to my bank account from India or from US, it should always show $100. So both the database servers storing the data should show the exact same value. That's known as guarantee of transaction or integrity. Some of the use cases of relational database are banking and healthcare applications. So payment gateways, payment modules of an e-commerce app, payment module of credit card management app, payment module of your banking apps. They will all follow relational database. With that being said, now let's take a look at the next slide. Some of the examples of relational databases are as follows. You have MySQL database, Oracle database, PostgreSQL database, MariaDB, and SQLite. They are all relational databases. They all provide these two properties. They allow you to structure your data, and they provide guarantee of transaction, and they provide you with asset compliance. That's the advantage of using a relational database. Now you may wonder, well, what are the disadvantages of using a relational database? So there are limits to how well a relational database can scale. And that's where our friend non-relational database comes into picture. Note that there are organizations that have been able to successfully use relational database and scale. But that's for some other time. Let's now summarize what we have learned so far in this session. So we'll learn what is a relational database, what is a database transaction, what are the asset properties of relational database, when to use a relational database. We also studied some of the key studies of relational databases, banking apps and healthcare apps. We also learned what are the advantages and disadvantages of using a relational database. That's it for this session. Hope you enjoyed this session. I'll see you in the next one. Stay tuned. Bye. Hi there, this is Prathamesh, and in this session we'll learn more about non-relational databases. Let's take a look at what a non-relational database is and the different types of non-relational database. So a NoSQL database, also known as non-relational database, is where you do not store data necessarily in tables and rows. There are no keys like a relational database. It uses a storage model that's optimized for specific requirements of the type of data that's being stored. And there are different types of storage models, such as document storage model, key value storage model, so on and so forth. So the different types of non-relational databases are as follows. You have columnar database. In this case, the data is stored in different columns. A good example of columnar database is Cassandra. The next one is document database. In this case, the data is actually stored in documents. Some of the examples of document database are MongoDB and CouchDB. Next one is key-value database. This is one of the simplest type of non-relational databases. In this case, data is stored in the form of key-value pairs. Last but not the least, graph database. This database is typically used by social media networks because it's really efficient in storing connections between different elements of databases. Now, let's take a look at the next slide. So, you must be wondering when to use a non-relational database. The answer is, if you're planning to do rapid prototyping where you do not have a fixed schema or an attribute. Let's say you're trying to build an app for a school or a university, and you're not sure what attributes related to a student that you're going to store in this database. Then, for rapid prototyping, you can use a non-relational database. The next criteria is, let's say if you're looking for a database that has a low latency, you will go with non-relational database. Last but not the least, if you want to scale your database to support millions of users, please go with non-relational database. Note that even the relational databases can be scaled. It's just the operation to scale relational database is relatively complex compared to non-relational database. Now, with that being done, let's take a look at the next slide. So, the first type of non-relational database that we are going to select today and read about it is columnar database. In this case, the data is stored in the form of columns. These allows for quicker scans compared to a relational database. You must be wondering when to use a columnar database. The answer is simple. If you're looking to store profiles of different users, meaning if you're looking to store different objects which have similar attributes, go with relational database. So, in the case of social media users, each user will have a certain set of attributes: name, location, likes and dislikes in terms of groups, so on and so forth. All of that information can be stored in a columnar database. The second example is analytics. Let's say if you're performing analytics or if you're putting together different reports. In this case, you can go with columnar databases. Last but not the least, logs. Let's say your application is generating a lot of logs related to your infrastructure, your application, your users. All of those logs can be stored in a columnar database. A good example of columnar databases are as follows. Facebook provides Cassandra, which is Facebook's version of columnar database. There's an Apache HBase, and Google also provides a columnar database. It's known as Bigtable. If you understand what a columnar database is, now let's take a look at the next one, which is key-value data store. Key-value data store is by far the simplest of all the NoSQL databases. Here, the data is stored in the form of key-value pairs. It's the least complex of all the NoSQL databases. It's simple and it's scalable. Examples of key-value database stores are Redis, Amazon DynamoDB. Over here, you'll see a simple illustration of a key-value database. So data is stored in the form of key and value pairs. So in this case, we are storing different types of keys. So you have a name key that stores the value, which is Bob Simons. You have the birthday key, which stores the birth date of the person, which is Feb 11, let's say 1800. Then you have hobbies as a key, which stores different hobbies of an individual. In this case, this person has a hobby of stargazing. Now, if you understand what a key-value database is, let's try to understand the next type of NoSQL database, which is document database. In document database, data is actually stored in the form of documents. This kind of database is good for e-commerce and newspaper applications where each item will probably have a different attribute. So let's take an example of Amazon or eBay. Here you have different types of items that are stored in the database. Each of these items, let's say shirt and laptop, has their own attributes. So for this kind of databases, you will use document database. The way the information is stored in the document database is as follows. So let's say you have shirt. A shirt will have different types of attributes, let's say size, color, price, etc. All of those attributes can be stored in a document database. Next, you have laptop. A laptop will have different types of attributes: manufacturer, CPU, RAM, so on and so forth. That information can be stored in the document database. Let's say you have another item which is book. A book will have different types of attributes: title, author, publishing date, so on and so forth. All of that information can be stored easily in the document database. So to summarize, you use document database when you want to store items that have different attributes. If you understand this, let's take a look at the last type of database in the NoSQL category. This one is known as graph database. Graph database is one of the most complex type of NoSQL database. In this case, data is actually stored in the form of graph. It is designed to efficiently store relations between different entities. You use this when the data is interconnected. Let's take an example of purchasing and manufacturing system. Let's say there are systems that are providing you with different objects and items. There's a purchasing department and there's a manufacturing department. These two departments are interlinked, so that kind of data can be stored in graph database. Next, you have social media networks. You have users which are connected to each other, so that creates a connection, and this is where you can use a graph database. Last but not the least, scientific paper citations. Each paper that's published can be linked to 100 other papers because it has a lot of citations. That's another use case of graph database. So in these cases where you have different connections and where you're looking for NoSQL properties, scalability, low latency, so on and so forth, go with graph database. Graph database are most complex of all NoSQL database. You might be wondering who uses graph database. One of the companies that uses graph database is Facebook. Now, let's summarize what we have learned so far in this session. So we studied what is a non-relational database. We also studied different types of non-relational databases. We also studied when to use which type of non-relational database. I hope you enjoyed this session. I'll see you in the next session. Stay tuned. Hi there, this is Prathamesh, and in this session, we'll learn more about message queues. Before we try to understand what message queue is, let's try to understand how ATM machines work. Try to remember the last time you visited an ATM teller machine, also known as automated teller machine. It's a machine that dispenses cash or performs other banking services when an account holder inserts a bank card. Now let's assume while you are there, someone was already using the ATM machine. What do? Well, you actually join the queue. So in this case, the ATM machine was not available to you yet, so you decided to stand in queue. This means the ATM machine utilizes queue as a buffer for people, so it can potentially hold people for a specific amount of time and provide service to them per their position in the queue. Similarly, in the world of software service, what do you do when you have multiple software services that are running on the same server? And let's say one service needs to send a message to another service that is busy at the moment. You guessed it right. You add that message to the queue. In this case, software service A needs to send a message to software service B. Software service B is currently busy and can't process new messages. Now, software service A adds this message to the queue. Here, a message queue acts as a buffer and stores the message until the software service B is able to process those messages. This message queue solves two problems. One, it decouples service A from service B, meaning service A can now complete its work and put the output in message queue, and service B can take those messages once it's ready to process the messages. So, it decouples service A from service B. Second, this allows us to keep processing incoming messages and thereby allows us to process those requests received from the user without saying no to the user. Now let's take a look at the logical components of queue. Each message queue has four components. First is the producer. Producer is a service that generates the message and adds those to the queue. Second, we have a consumer. Consumer is a service that extracts those messages and processes them. Third, we have the message queue. This holds the message and acts as a buffer. Fourth, we have messages. That is the data that is being sent from one service to another. In case of message queue, each message can only be sent to one consumer. What if you have a scenario where you need to send each message to multiple consumers? Can you think about this scenario? What about social media notifications? Let's say you add a new post and your social media service will need to be sent. Your social media service will need to send notifications related to that post to all your connections. That's a one-to-many use case. How do you handle that? In that case, you will need PubSub system, also known as Publisher Subscriber System. A Publisher Subscriber System allows you to send your message to multiple consumers. One producer can produce the message, and the message will be stored in the queue until all of your consumers are able to extract that message and process it. Thus, now you can use this component to provide social media notification functionality to your users. Now let's summarize what we have learned so far. We learned first, what is a message queue? A message queue is a form of asynchronous service-to-service communication. It decouples the functionality of one service from another. Why do we need message queue? We need message queue because it allows two services to communicate with each other without getting blocked by the response. How does a message queue work? A message queue works by adding messages to the queue and storing them until a consumer is able to actually process those messages. So it actually acts like a buffer. What are the advantages of using a message queue? One, it allows you to decouple different services in your architecture. Number two, it allows you to scale. What are the disadvantages? Disadvantages, it adds slight amount of complexity in your architecture. Now, in order to implement these message queues, you will need message brokers, also known as softwares, message broker softwares. Some of the common examples are RabbitMQ, Apache Kafka, and Amazon SQS. If you are using a cloud-based solution, you can go with Amazon SQS. If you are using an on-prem solution, or if you're using a solution where you are not necessarily using Amazon SQS, you can choose between either RabbitMQ or Apache Kafka. RabbitMQ is used typically where you need a response that includes low latency. Apache Kafka is used for streaming data. If you have a lot of data, let's say logs that are being generated every single second, then go with Apache Kafka. That's it for this session. I hope you enjoyed this session. I'll see you in the next session. Stay tuned. Hi there, this is Prathamesh, and in this session, we'll learn a reference framework you can use to design systems from scratch. Remember that there is no right or wrong design. Design is either good or has areas for improvement. There are different ways to design a system. This is just one of the many approaches you can follow to design a system. Now, let's get started. The first step involved in the system design process is learning more about the goals and the requirements for the system. As a developer, architect, student, or a founder, you should always ask this question so you can learn the motivation behind designing the system. What problems are we trying to solve by designing the systems? Whom are we trying to solve this problem for? What are we solving this problem? These questions will help you understand the vision behind building this system. Once you know what the vision is and who the users are, then we should clarify the requirements. What are our functional requirements? Meaning, what are the key features we'll need to provide to our end users? What are our non-functional requirements? What kind of scale are we looking at? Are we designing the system for 100 users, for 1 million users, or for 1 billion users? What kind of latency are we looking at? Similarly, we should understand what kind of availability and reliability do we need for the system. Let's try to understand what availability means. Availability means what percentage of time is my system available for end users, meaning what percentage of time is my system actually up and running. So what does 99.9% availability mean? It means 99.9% of time over 1 year, meaning over 365 days, my system will be up and running for my end users. So my possible downtimes are as follows. Daily, 1 minute 26 seconds. weekly 10 minutes 5 seconds, monthly 43 minutes and 12 seconds. And over a period of 365 days, that is 1 year, I can expect to have a downtime of roughly 8 hours 45 minutes 36 seconds if I'm claiming that my system has a 99.9% availability. Now if you understand this, let's take a look at step 2 in system design. The next step involved in the system design is understanding the traffic and the capacity estimates. Trying to figure out what is the number of users for whom we are designing this app for. How many users will use this app? What are my daily active users? How many web servers do I need to run this app and to support that scale? How many database servers do I need to store that data? What are my traffic and storage requirements for this app in terms of requests per second or in terms of terabytes and petabytes? Once you have a clear knowledge about your traffic and capacity estimates, then you can move on to the next step. Now that we have learned the goals, the requirements, the capacity estimates, let's try to understand the third step, which is essentially the high-level system design. In this step, we are going to do two things. One, first we are going to put together a high-level system design based on the requirements that we have learned so far. This is where we choose the system components for the requirements of a system and build the system. In addition to choosing the right components, we'll also need to choose appropriate protocols. There are different types of protocols, and each of these protocols provide different functionality. Let's say you're building a basic web app that allows students to enroll in a university course. This is a simple read and write operation, so you can choose HTTP, which is a hypertext transfer protocol. This protocol allows you to exchange information between a web client and a web server. Now, what if you want to secure this data? Meaning, you want to securely exchange this data between the client and the server. Well, you can use HTTPS. The S over there stands for security. It adds an additional layer of security by using protocols such as TLS and SSL. These are security protocols. Wait a minute, what if you are building a web application like WhatsApp, where you need to implement the duplex mode of communication between the server and the client? Meaning, a client should be able to send a message to the server, and the server should be able to send a message back to the client. That's where you can use WebSocket. Protocols like WebSocket allow your end users to maintain a persistent connection with the server, so you don't have to continuously establish and break sessions. What if you are using a language for coding in which WebSocket is not supported? That's where you can use long polling. Long polling is an alternative protocol to WebSocket, but it has its own disadvantages. The last two protocols are RPC and gRPC. RPC stands for Remote Procedure Calls, and gRPC is nothing but Google's version of Remote Procedure Calls. In short, RPC is used by software services to communicate with each other in a distributed system by abstracting the network layer. So let's say you have multiple software services running on different servers which are connected through different networks. What if you wanted to abstract that network layer? Meaning, what if you didn't want it to worry about those network layers and still allow the software services to communicate with each other? That's where you'll go with RPC or gRPC. WebRTC, on the other hand, is used for video chat services. So let's say you want to schedule a Zoom call, Google Meet call, Skype call, or you want to build an application that allows you to provide this video chat functionality. This is where you can use WebRTC. What if you want to provide video streaming services such as Netflix, Disney+, Hulu? This is where you can use streaming protocols such as Dash, ITMP, and WebRTC. Now that you have a high-level understanding about what the design should be and what the protocols are, and when to use which protocol, let's take a look at the fourth step. This is probably one of the most crucial steps in designing the system. This is where you're going to choose databases. If you haven't already watched the database section, I highly recommend you please go through that session and then come back to this framework. Choosing the right database is going to be crucial in your system design. At a high level, there are two types of databases, relational and non-relational. You would use relational database where you need two things. One, ACID compliance, meaning ACID properties, and two, guarantee of transactions or integrity. You can use non-relational database when you're looking for two things. One is high scalable environment, and second, flexible schema, meaning if you're trying to do rapid prototyping. That's where you go for non-relational database. What are the different types of relational database? So some of the common examples of relational databases are MySQL, PostgreSQL, MariaDB. These relational databases are typically used in payments and banking apps. This is where you want to ensure there's a guarantee of transaction, meaning if a money has been deducted from a certain bank account, it has to be reflected across all the servers that are reporting the information associated with that bank account. So there's consistency, there's reliability, there's integrity, and there's honesty. That's why you need relational database. Again, if you want to learn more about these databases, I highly recommend you take a look at the database session if you haven't already done so. Next is non-relational databases. Use non-relational databases when you're looking for high scalability and when you want to have your schema, which is flexible. There are four different types of non-relational databases. One is columnar database. A good example of this is Cassandra. You use columnar database if you are building a reporting app, analytics app, or a social media network. Second type of database is document database. You use document database if you are building an e-commerce app. So in the case of e-commerce app, you have different types of objects that you have to store. Each of these objects have different attributes. So a refrigerator will have different attributes compared to a shirt. A laptop would have a different attribute compared to a cell phone. What I mean by attribute are the properties. So a shirt will have different attributes such as color, size, shape, so on and so forth. On these occasions, you should use document database. Some of the good examples of document database are MongoDB and CouchDB. Third, you have graph database. This is probably one of the most complex database to implement. But this comes handy when you have a lot of connections between different entities. Some of the good examples of graph database are, let's say, social media network. You have multiple users, each user is connected to another user, so this creates a huge connection graph, and this is where you use graph database. Another example is scientific reports. Each of the scientific reports will include different citations, and each of these reports are connected to different citations, so there are a lot of connections. That's where you use graph database. Last but not the least is the simplest of all non-relational databases. That's key value store. Some of the examples of key value store are Redis, Amazon DynamoDB. Now, once you have made an appropriate choice of database, we'll move on to the next step. This is the fifth step in the system design framework. This is where you will finalize your bottlenecks and trade-offs. What is bottleneck? So bottleneck is a single point of failure in your design. So in this step, we'll try to identify what are our single point of failures and how can we prevent them and how can we resolve them. Next, trade-offs. Building a system involves trade-offs. There are trade-offs that you make on the budget front, there are trade-offs that you make on the functionality front, there are trade-offs that you make on the reliability of the system. So every system has a trade-off. One way of looking at trade-offs is CAP theorem. CAP theorem, CAP stands for consistency, availability, and partition tolerance. What CAP theorem says is that if you have a distributed system, meaning if your software is installed across a bunch of different servers, and if you have different services running on each of these servers, then you can only provide two of these three properties. So you can either provide CNA, which is consistency or availability, or you can provide availability and partition tolerance, or you can provide consistency and partition tolerance. You cannot provide all three properties. Why? Because that would break the system. So let's take a look at each of these properties. Consistency. What consistency means is that data should be consistent across multiple servers. A good example to understand this is, let's assume you are maintaining a bank account. Let's say your bank account balance today is $100. Now, you access your bank account from US, which shows $100. Let's say your friend has access to your bank account and they are in Asia and they try to access the same bank account. Now, they are connected to a server that's close to Asia. But both the servers in US and Asia should actually reflect the same bank account balance. That's known as consistency. Availability, that's the second property. This means no matter what, my software guarantees a response for every single request that's sent to a software. A good example of this is I should be able to log into my bank account no matter what time of the day and what location I'm trying to access the bank account. That's availability. Last but not the least is partition tolerance. What this means is your system is partition tolerant if it works, even if the link between the server goes down. Meaning if you have multiple servers and if the link between some of these servers goes down, if the network link goes down, you still expect your system to work. That's known as partition tolerance. Now you may ask, well, why can't I provide consistency and partition tolerance at the same time along with availability? The answer is simple. Let's assume you have 3 servers. Let's assume they have 2 links, one between each server. If the link between the servers go down, these servers won't be able to synchronize among themselves. So they won't be consistent. They will have different information. And that's where you break the consistency loop. So, in theory, CAP theorem says you can only provide 2 out of these 3 properties. Now that you understand the bottlenecks and the trade-offs, let's try to move on to the next step. Last step involved in system design is basically understanding the success of a product. So let's say you have designed the system we are about to launch a product. How are you going to measure how well your product has been designed and how well it's performing? This is where all of these metrics will come into picture. So the first metric is happiness metrics. Are my customers happy? The second metric is engagement metric. How frequently do my customers use my product? Adoption metrics. How many new customers did we onboard this last quarter or this last month? Fourth, retention. What percentage of our customers from the previous quarter are we able to retain this quarter? That's retention. Last but not the least is the termination metrics. What percentage of our customers canceled their subscription service this last quarter? That's termination metric. So, in this particular course, so far we have understood the 6 steps involved in the system design, and this actually seals a system design framework. I hope you enjoyed this session. I will see you in the next session. Stay tuned. Hi there, I welcome you all to this session. In this session, we are going to learn the system design of WhatsApp. Again, this is a high-level overview of the system design for WhatsApp. Let's get started. We'll follow a system design framework. Our first step involved in system design is clarifying goals. So let's say our goal over here is to design WhatsApp. As usual, we are going to ask some follow-up questions. Why are we designing the system? Who are we designing the system for? What's our vision? How many users do we need to design this application for? Are we looking at a specific target segment, such as professionals, students, or teenagers? What is the scale we're looking at? Do we want this system to be designed for 1 billion users, 100 million users, or 10 users? Let's assume in this case we are designing WhatsApp for 1 billion global users. Let's move on to the next step, which is step 2. In this step, we are going to finalize requirements and we are going to do some capacity and scale estimates. First, functional requirements. Let's try to understand what our functional requirements are. Let's assume in this case, following are the requirements that we need. 1. We want our users to be able to send one-on-one messages to other users. Second, we want our users to be able to check the status of different users, whether they're online or offline. Third, read receipts. Here, we want the users to be able to receive an acknowledgement from other users as to whether they have read their message or not. Last but not the least, we want our users to be able to upload and download images through WhatsApp. Now let's take a look at non-functional requirements. Non-functional requirements are the requirements that you cannot necessarily see through your eye, but you can feel those as you use these apps. So some of the key requirements associated with WhatsApp are low latency. We want real-time response between two different users. High availability. We want to make sure that users are able to access this service at any given point of time. Scalability. As our user base grows, we should be able to grow our system, meaning we should be able to add more servers. And last but not the least, security. We want to make sure all of the messages that are exchanged between different users are encrypted. Now that we know what the functional and the non-functional requirements are, let's take a look at capacity estimates. The goal of essentially trying to figure out capacity estimates is we are trying to estimate what are the number of application and database servers we'll need to build the system. This will help us understand how much amount of budget or cost is needed to build this system. First, we'll try to figure out what our traffic estimates are. In simple terms, this means the total number of requests that can be handled by your application. Let's assume we have 1 billion total users, and let's assume 30% of those are daily active users. That brings us to 300 million daily active users. Let's assume 30% of these 300 million are located in Asia, 30% in Europe, and 30% in North America. With that as a background now, you will have the maximum peak request per second is equal to 30% of 300 million, that's 90 million requests per second. The reason being, your users in Asia, your users in Europe, and your users in North America, each of these three classes of users, they are operating on different time zones. So at any given point of time for that particular time zone, the peak number of users will be the peak number of users that belong to that class. That's 30% of 300 million, hence 90 million requests per second. That's the maximum number of requests that your servers will need to handle. From this equation, we can figure out the number of servers that we'll need. How? We know that the maximum number of requests that a server can handle, a standard generic server, industrial server that can handle is 100,000 requests per second. And this is of course assuming without any tweaks and optimizations. If you do tweak and optimizations, a server can typically handle roughly about 1 million to 2 million requests per second. Storage estimates. This is basically where we try to figure out the space that's required to store database of all the users for the next years, for the next 10 years. Let's assume we have 90 million users out here. Each of these users are trying to exchange 5 messages per day, and each message includes 150 characters. Why? Let's assume it's similar to SMS, so 140 characters. And each character needs about 2 bytes. The total storage needed per day is 90 million multiplied by 5 messages per day, multiplied by 140 characters per message, multiplied by 2 bytes. That's 126 gigabyte. Now, that's per day. So for per year, we'll multiply that by 365, so that's 46 terabytes. Now that's per year. Let's assume we want to take into account the total storage we'll need for 10 years. That's 46 into 10, that's 460 terabytes. And this is just for text messages. We haven't yet taken into account the media storage. But in reality, we can perform the similar computations for media storage. For example, we can assume each of those 90 million users is sharing one picture a day, and the size of each picture and image is roughly about 4 megabytes. And from that, we can compute the total media storage we'll need to build this system. Now let's move on to step 3. This is the most crucial step involved in the system design. In this case, for simplicity, we'll assume we are using MySQL database. But in reality, as we all know, WhatsApp has 1 billion users. It requires low latency and high scalability, so we can go with columnar database. A good example of columnar database would be Cassandra. Once we finalize the type of database, we'll have to model the data, meaning we'll have to figure out how many tables we need, which table will have what kind of information. Let's assume for simplicity we need 3 tables. One that stores the relationship between a user and the server, meaning we have 1 million users and we have multiple servers. We need to keep a track of which user is connected to which server. That's where table 1 will come into picture. Table 2 is the conversation table. This table connects a user to a conversation ID and an encryption key. This is the table where we'll store encryption key for every conversation. This is the key that will be used to encrypt, meaning to secure that conversation. Last but not the least is the conversation table itself. This is where you will have the actual text that's exchanged between two different users. So let's say user A sends hi to user B. That's going to be your text that's going from user A to user B, and that's slated for a particular time. That will be stored in conversation table. So we're using MySQL database for simplicity, and we are going to use 3 different tables to store our data. Now that being done, let's take a look at our fourth step, which is high-level system design. So this is just a very high-level overview of our design. If we were to build a basic system for WhatsApp, this is what it would look like. Let's try to understand how the system works from bottom to up. At the bottom layer, you have all your users, which are people like you and me who use WhatsApp on their phones. So you have 3 users, user A, user B, and user C. When they try to access WhatsApp, the requests are first sent to load balancer. Load balancer, as we know from our system design course, will transfer this request to a particular server based on the load of those servers. So let's say user A tries to send a message to user B. First, the request from user A goes to the load balancer. Load balancer will send this request to server A or server 1. Server 1 will add this to the Redis cache or to the Redis database. Over here, basically it will track server A is serving user A, and this is the timestamp. Now, user B will connect to the system. Let's say load balancer connects user B to server 2. Server 2 will track user B and will add this information in the database on the top right corner of the screen. So you will have user B connected to server 2. Now, when user A sends a message to user B, the message first goes to server 1. Server 1 takes a look at this Redis cache and figures out where is user B. It comes to know that user B is connected to server 2. Then it forwards that message to server 2. Server 2 then forwards that message to user B. Thus, a message is transferred from user A to user B. Now, before we proceed further, let's take a look at all the components. At the bottom half, you have all the clients, which are basically your users. Then you have load balancer, which distributes the load, the incoming request amongst different servers. Then you have the servers themselves, which essentially process your request, which is where you have all your API calls. Then you have on the top database server. This is where you store all your data. Then you have the file storage server on the top left corner. This is where you will store all your image files. So let's say if user A sends image to user B, that will be stored in this file storage server S3 server. Now you must be wondering what protocol are we using out here for communication between a client and a server. From our course, you know that in this particular session we are designing WhatsApp. So what we are looking at is bidirectional communication between the client and the server, and we need to maintain a persistent connection so we can provide real-time service to our end user. And one of the protocols that provides this service is WebSockets. So in this case, the users are going to connect to the server over the WebSocket protocol because it allows us to maintain an end-to-end connection for longer duration, and at the same time, it allows for bidirectional transfer of messages between client and server and client. Now, let's take a look at the next slide. Here, we are going to discuss 3 different scenarios. Let's say, first scenario, user A and user B, they are both online. User A sends a message to user B. This message first goes to load balancer. From load balancer, it goes to server 1, assuming user A is connected to server 1. Server 1 will take a look at the cache database to figure out where is user B connected to. It knows it's connected to server 2, so server 1 will forward the message to server 2. Server 2 will then forward the message to user B, and user B will receive this message. Let's assume user A is now online but user B is offline, and user A sends the message to user B. What happens in this case? In this case, the message goes to server 1. Server 1 tries to find the location of user B, and it's not able to find it. Why? Because user B is offline, so it's not connected to any server. In this case, server 1 will store this message in the database. Now, what happens when user B comes online? When user B comes online, let's assume it gets connected to server 2. In this case, as soon as user B gets connected to server 2 will try to figure out if there are any unread messages or undelivered messages that have to be sent to user B. So it will check the database, and yes, there is a message from user A, and it will send that message to user B. And this is what I mean by bidirectional communication, meaning in this case, the server proactively sent a message to the user as soon as the user came online. And this is where the WebSocket protocol comes in handy. Now that we know at a very high level how WhatsApp works, let's take a look at how the real system was designed by the WhatsApp engineers. Before we take a look at that, we'll take a quick look at the bottlenecks and the trade-offs in this design. Bottleneck, as we know from our course, is a single point of failure. So in this particular case, what's a single component that fails that can actually fail the entire system? If it fails, it can fail the entire system. In this case, the single component that can cause a single point of failure is load balancer. So if this load balancer goes down, our system will go down, so that's a bottleneck. How can we overcome that? Well, we can deploy multiple load balancer. What are the trade-offs? Well, if we deploy multiple load balancer, we are going to add complexity in our system. But the advantage is we are providing higher reliability. So, as you know, in any system you'll have to make trade-offs, whether it's budget, whether it's availability, whether it's reliability, so on and so forth. So choose your system components accordingly and choose your protocols accordingly. Now let's take a look at the original WhatsApp design. So at a high level, WhatsApp at one point supported 450 million customers, and today it supports roughly about 1 billion active users. At the time, it had a system design team and an engineering team with just 32 engineers. These 32 engineers tweaked each server so it could support up to 2 million connections versus a normal server that can serve anywhere about 100 connections per second without any optimizations. The operating system that was chosen back in the day was FreeBSD. The language that they chose was Erlang. The backend system, meaning the system that connects to API that they chose, was essentially encoded using PHP and Erlang. There is a lot to this design that's hard to summarize in this particular presentation. So I highly encourage you to take a look at this article that is published on this website. I personally found this to be extremely helpful in understanding the design of the WhatsApp at a high level. I hope you enjoyed this session, and I hope you enjoyed this course. I'll try my best to add new system designs and case studies in this particular course, so stay tuned.